Okay, right. So all right. So today we're going to look at the next theorem. Okay. So the notation we're going to use now is. Give me a second. This standard bug being one node. Okay. So the notation we're going to use today is the following. So L is the set of linear operators from the vector space V to vector space W, right? And the text emphasizes that L is only defined when V and W are vector spaces over the same field. Okay, so you cannot have. So when we're writing this notation, we're assuming that the vector spaces are defined over the same field. So let's start with theorem 5. So theorem 5 says let V be an n-dimensional vector space. Okay, if you're, please take a minute to silence your phones. It would help. Okay, so let V be an n-dimensional vector space over the field F. Let W be an m-dimensional vector space over the field F as well. Okay. Then the claim is that the space of linear operators from V to W is going to be finite dimensional, and it will have dimension m times n. Okay, is the theorem statement okay? Does it make sense? Yeah. Okay. So let's start. Okay. So now the strategy is that we will construct a very simple basis for capital F for the set of linear operators from V to W. So let's see how to do that. So suppose that B is some ordered basis for V and B prime is some ordered basis for W. Okay. L is so here, okay. So this is the notation. So L here is the space of linear transformations from the vector space V to the vector space W. Okay. So what we are trying to claim is that this space L is actually a finite dimensional vector space, and it will have this specific dimension. Yeah, I guess in the previous theorems we already, what did we show last time? Yeah, so last time we already established, right, that the set of all linear transformations from V to W, together with these operations that we described, form a vector space. So this we had already established. Now what we're doing is we are saying that if you know something about the dimensions of V and W, so in particular, if you know that V is an n-dimensional space and W is an m-dimensional space, not only do we know that this L, the set of linear operators, is going to form a vector space, we also know what the dimension of this vector space will be. Okay. So that is what we are trying to show here. So let us denote by B, capital V, set basis for V, and then by capital V prime, the basis for W. Yep. Okay. Now for each pair of integrals P comma Q, where P and Q are between M and N, one can define a linear transformation EP comma Q from V to W using this definition. So what is this definition saying? So let's try to understand this. This is basically, okay, so this definition is P comma Q on alpha I is defined to be delta IQ beta P. So what does that mean? It means that, oh, sorry, there's some problem with screen sharing. Okay. So what we're trying to say here is that you take the basis element alpha I from the basis B, okay? And what this EPQ is going to do is it will map the vector alpha Q to the vector beta P, okay? And everything else will be mapped to the zero vector. Yeah? Is that okay? Because you see, the index I, when this index I is different from Q, this delta will disappear, right? So you know the delta function, right? So the delta function is defined to be, so delta AP is defined to be 1 when A equals B and 0 otherwise. Right? Is that okay? So now when you put this, when you apply this map, right? When this I does not match Q, so when this index I does not match the index Q, this map will give you 0, right? And when it does now, it will replace, so this will become 1. So when I equals q, okay, this thing will be what you get. Okay, so what it is doing effectively is it's mapping alpha q to beta p, and it is mapping everything else to 0. Is the definition map clear? Can I have a show of hands on this side for those who are following? Okay, is it clear? Okay, great. So now according to theorem 1, there is a unique transformation from V to W that satisfies these conditions. So what was theorem 1 actually about? So let's see what theorem 1 was. Okay, so theorem 1 says the following. So the theorem, it says that there's precisely one linear transformation that takes you from the basis of E to the basis of W. Okay, so this was the first theorem we proved. Is you have some vectors, some basis in V, and you have some basis in W, and you're mapping the linear transformation is just mapping that basis from V to W. Then this mapping is unique. That is what the mistake is. Right, so we're going to use that fact now. Okay, so we're going to use that fact. So we've said that, okay, we are going to define some mapping here, which is mapping the basis of V to the basis of W. And so therefore, there must be a unique linear transformation from V to W, right? Because once you specify how the basis moves, you specified how the entire transformation moves. Okay, all right. So now, here's the next claim. So the claim is that the mn transformations EPQ. So there are mn transformations. Why? Because so P and Q are indices, right? So P, remember, is from 1 to n, right? And Q is from 1 to n. So in total, there are m times n transformations, right? Okay. So these transformations, the claim is that they form a basis for the set of all linear transformations from V to W. Right? Is it making sense what we're trying to do here? So you have this set of all linear transformations. We want to construct a basis using which we can express all possible linear transformations. Right? So it is, so the claim, what they're trying to argue is that this is basically going to form a basis. So EPQ, which are very specific maps that we define, they will be the basis of the linear transformation. No? Any questions? Okay. All right. So then let T be a linear transformation from V to W. Okay. For each J in 1 to n, let Aij to Emj be the coordinates of the vector Tj, T alpha j, T acting on alpha j, in the ordered basis Vj. So what does that mean? So you take this vector T alpha j and you express it as a linear combination of the basis in vector space W. Right? Because T alpha takes a vector in, so T takes a vector in V and maps it to a vector in W. We already have a basis for W, so we can always expand any vector in the basis of W. Right? Is that okay? All right. So we've expanded. So we've expanded this vector in the basis of W. So we've not really done much. And for each J, we'll have like some different coefficients, right? So we're adding those. We're adding the index J. Is that okay? Okay, so what do we want to show? We want to show that this transformation T can be expressed as a linear combination of P, PQ, which basically form the basis, right? That's what we want to argue. So we're saying that every linear transformation T can be expressed as a linear combination of the transformations in PQ. That's what we're trying to do. Is it making sense? Any questions? Right. So what we're now trying to do, so this is the claim that we're trying to show. We're trying to show that this object EPQ forms a basis for the set of all linear transformations from V to W. Okay. So why are we trying to do this? We want to establish that that L, the space L of all linear operators from V to W has a dimension m times n. And the proof technique we are using is we are going to show a basis, and we'll say that the basis is has these many elements. Okay, so it's being done explicitly by construction, and we already specified the elements that are going to form the basis. So we specified this map EPQ. And now what we're trying to argue is that you can express any T as a linear combination of these EPQs. Okay, that is what we do. Is it making sense? Yeah. Okay. So let's see how to do this. So let U be the linear transformation in the right hand side above. Okay, so it is this linear transformation. Okay. Then for each J, the following holds. So one can write Uj. Okay, so it's this linear transformation. So one can write U acting on alpha J as follows. So we basically write down, this is just by definition, right? So okay, let me write it down because it might be a little bit easier. EQ, right? So I'm just writing the definition of EPQ when you have alpha J. This is sum of P, sum of Q, APQ, delta JQ, beta P. Right? So what I did here was I just applied the definition of EPQ acting on some vector alpha J. Right? So, okay, so I applied the definition. Now we have a sum over, so this is a very simple property of the delta function, right? Because I'm summing over Q, what this would give you is a Pj, sum over Q. Right, because the delta function is 0 unless I and Q merge. So what that means is I can substitute, sorry, J and Q merge, right? Otherwise the delta function is 0. So when I sum, the only terms that would contribute are the ones for which Q actually matches J. So I say it again. Yeah, APQ is any constant. Yeah. It's just a scalar. Exactly. Is that okay? Is it making sense? All right. Okay, and then when you do the sum, we would get APJ and then beta P. I've just done substitution, and beta P remains the same. And now what is this object? This object is T alpha J. Right? So if you look at equation 3.1, this was exactly how we said the action of TJ is. Right? So what we have shown is that indeed this operation that we wrote, this linear combination, when you apply it in any vector alpha J, the action is exactly the same as applying on T, applying alpha J, applying T on the vector alpha J. Is that okay? I'll give you a minute to make sure that everything is clear. You can ask me if something's not clear, because I can repeat if you missed something. It's not a problem. APJ, this. Okay, so APJ, so A, remember, are just these coefficients, right, that we already introduced. So it's just, it's a slight function, right? So that's fine. And here what we're saying is APQ delta JQ sum over Q. So I was claiming that this is the same as APJ, right? And why that is basically you can expand. You can just use the definition, right? So this object, this is 0 unless Q equals J, correct? So when you expand the sum, the only terms that would contribute are the ones where J matches Q. And so it would be exactly 110. So that's all we did. It's going from here to here, we just use the sum on sum over Q, and we noted that the only term that would contribute is the J term. That's all. Is that okay? Sorry, I didn't catch that. Let me write down what you're saying. Say it again, say it slowly. In the function APQ, you're multiplying to APQ and beta. Yeah, but this is just a scalar, right? So yeah, so I'm just saying that this expression, right? These are just numbers. So I'm just writing the condition on the numbers, right? I can do the sum. So I can just isolate this part, right? So I'm just focusing on this part and I'm applying this identity. Okay, these are just scalars. So any other questions? Is it all right? Okay, so let's continue then. So what have we established? We have established that every t can be written as a linear combination of these guys, of these EPQs. Okay, so effectively we know that EPQ basically spans. The span of EPQ is basically the same as the set of all linear operators from V to W, because we can express any one of them in this form. And remember, to show a basis, there are two requirements, right? One is that it spans the space, and the second is that they're linearly independent. So now we're going to establish that EPQ are actually linearly independent. Okay? So let's do that. So we want to show that no linear combination of EPQs can give you the zero vector unless all the coefficients are zero. Right? That's just the definition. And the claim is that this also follows from this equation that we wrote down 3, 2 here. Okay. So let's look at it more carefully. So the equation was basically just this, right? So suppose that there is some operator u that we write in this form, right? And suppose this is what is the zero transform, right? So this is the thing that will give you zeros. So what that means is that u acting on any vector alpha j should give you the zero vector. Okay. And what does that mean? It means that this linear combination for I think I messed up the index. I suppose this should be j. Isn't it? Wait, what did it? Okay, let's apply the transformation. Let's do it properly. So PQ, APQ, EPQ. Okay. Acting on alpha j is 0. Okay, the EPQ we just computed. So yeah, so this entire object from our definition will just give you APJ sum over P. Okay, so I messed up. So this index should be okay. Okay, so what we're getting is that a linear combination of vectors in beta in W, right? The basis vectors in W, they have to give you a 0, and the only way this can happen is when all APJs are 0. Right? Because beta is already a linearly independent basis for W. So the only way a bunch of linearly independent vectors sum to 0 is when all the coefficients are 0. Right? And we can repeat this argument. So we can repeat this for every alpha j. Right? So what that would give is that for every p and every j, these coefficients have to be 0. Okay. So what does that show? What does that tell us? That tells us that this EPQ, these are linearly independent, because there is no linear combination of these EPQs that would give you a 0 vector. And how did we prove it? We said that suppose there was some operator which was a linear combination of these guys that gave you 0, then we showed that in that case all of these coefficients would have to be 0. And what property did we use? We used the fact that beta is a basis for W. Okay. Is that okay? Does that make sense? And who else was following on this side other than you two? Is anyone else following on this side? Okay. Okay. So for you two, it's fine. Good. Okay. So let's continue then. Right. So what is that? It establishes that EPQ is a basis, right? So we said it spans the space and it's linearly independent. We established both properties. So that means EPQ is a basis. And the size of the basis is clearly Mn, right? Because P and Q go from 1 to M and 1 to N. And that means the dimension of the space is Mn, as we accepted. So now let's look at the next. Sorry, I don't know why the screen share keeps stopping. See? Okay. All right. So the next thing you're going to do is we look at theorem 6. So theorem 6 says the following. So suppose V, W, and Z are vector spaces over the field capital F. Okay? And let T be some linear transformation from V to W, and U is some linear transformation from W to Z. Okay, so you have VW, T is taking you from V to W, and U is taking you from W to Z. Okay, so those are the vector spaces. Then the composed functions, the UT defined as follows. So UT alpha is defined as applying T on alpha. Okay, so T belongs to V, T alpha is going to belong to W, and U takes vectors in W to Z. Okay, so everything is sort of well defined. So UT alpha, which is defined as follows, is a linear transformation from V to Z. Okay, so if T is a linear transformation and U is a linear transformation, then their composition is also a linear transformation. That is the claim. Is the statement okay? Okay. All right. So let's start then. So the proof is as follows. So UT, okay, so how do you prove something is a linear transformation? This is the definition, right? That any vector, so okay, so the transformation on C alpha beta has to be the same as CT alpha plus T beta, right? This is sort of the definition that you want to check, the property that you want to check. So let's see if this is the case. So you start with, using the definition. So this is just the definition of UT, right? Then you expand it. This is using the fact that T is a linear transformation, right? And this last one is doing what? It is applying the definition of U. No, wait, what did I do? No, ah, no, okay. This is using the fact that U is a linear transformation. Okay, and then this is using the definition of. Other steps clear? Right, it's very straightforward. There's nothing very deep. This proof is very, very easy. Any questions? Yeah. Okay. So let's start then. So now the story is that so from now we will primarily focus on linear transformations from V to itself. Okay, and we'll use a simpler notation. We'll just say T is a linear transformation on the vector space V itself. Okay, so we're not saying it's going from V to W. We focus on things that are not rotating. The definition is if V is a vector space over the field F, a linear operator on V is a linear transformation from V to. That's just the formally stating the definition. So in theorem 6, when V equals W equals Z, U and T are linear operators on V. Yeah, because we proved the theorem more gently. So we said for V, W, Z being potentially distinct. Now we're saying that let U, V, V, W, Z be the same vector spaces. And okay, so then if U and T are linear operators on V, it turns out that the composition is also a linear operator on V. Right? Because we don't have to worry about changing the domains. That's all. Okay. That's just a small note. The next one is that the space LVV, okay, so the space of linear operators from V to itself, has a multiplication defined on it by composition. Okay? So normally, so T square would basically be interpreted. So T square would basically be interpreted as T acting on T. Right? So because of the fact that it's on the same vector space, this is easy. Okay, and then the operator tu is also defined, and one should note that in general, ut and tu is not equal to 0. Okay, so not only can you apply t to itself, you can also compose t with the different map, and in general, these will not compute. Okay, so obviously this is like matrix multiplication. So we were well aware of multiple instances where this is not the case. So this one. And the final one is that if t is a linear operator on V, then one can compose t with t. Okay, so this we already saw. I think I messed up the order. Hold on. Okay. So now, because things are very well defined, t square and t to the n are going to be defined like this. T0 will be taken to be the identity as long as t is not 0. Okay. Okay. Right. So now let's state a lemma. So this lemma says the following. It says, let V be a vector space over the field F. Okay. Let U, T1 and T2 be linear operators on V. And let C be some element of capital F. Okay, so V is F. V is a vector space. U, T1, T2 going from V to V. They're linear operators, and C is some scalar. Okay. So then it says that the following properties hold. So it has identity times U is U times identity is U. So this is completely trivial. Okay, so this is fine. We just state it for emphasis. The second one is that U acting on T1 plus T2 is the same as the distributive property. So it doesn't really matter which order you do it in. And similarly, whether you do it on the right or the left. And finally, scalar multiplication. Okay, so these are like some of the basic things. So let's quickly do them because it's sort of nice to do it. Okay, I think the C part is anyway homework. Okay, so let's just do the B part. So here in the B part, what are we going to do? We're going to just apply the definition, right? So U acting on T1, so U on T1 plus T2, acting on alpha, right? This object is what we're going to do here as the first step is the definition of composition. So this would give us U acting on T1 plus T2 of alpha, right? The next step is applying the definition of T1 plus T2. So definition of T1 plus T2, right? So that was just T1 alpha plus T2 alpha. This stuff is very boring, but I promise this is probably the only ultra boring thing to do here. The rest of it should hopefully be more interesting. Yeah, and then so this part is fine. The next is we are just using linearity of U. Actually, I should ask you, okay, so what property are we using here? Maybe some of you didn't pay attention. So what property are we using in this step? Yeah, so we are using linearity, right? Because U is a linear operator, we can apply the definition, right? Okay. So it's a linear operator, so therefore we get what? We get U T1 alpha plus U T2 alpha. Okay. Okay, now what property are we using in going from here to here? Right. So here what we're using, we have to be a bit more precise, right? So we're using the definition of a composition. Right? Because the definition of a composition was that if you have U V acting on alpha, then this was defined as U acting on V of alpha. Right? So we're using that. We have to be careful, okay? Because when you're giving the reasons, it has to be you have to pinpoint which property you used. Okay, so it looks very, very trivial, but you have to be careful about what property you're going to use to argue this. Okay, and then the final step is right. So now you have UT1, UT2. This is okay, and now we can conclude that U acting on T1 plus T2 is the same as UT1 plus UT2. Right. This last one is using actually there's one more property, which is that we're using the sum property. Right? So we defined sum on linear operators. So we said that if you have T plus U, it is defined as the map. So T plus U acting on alpha, right? this was defined to be T alpha plus U alpha. So we're using that definition again over here. Okay, so you're using lots of different properties to get this very, very straightforward thing, but it's just good to be a little bit cautious. Okay, then you can proceed similarly. I'll not do this step. I'll not do this one. We'll leave it as an exercise. You essentially apply the same set of operations, but in the other directions. You start with U first, and then you get the final result. Okay. The last one is also similar. Okay, and it says that note that the proofs of these two distributive laws do not use the fact that T1 and T2 are linear. Okay, so then I got something really wrong. Okay, so here I claimed, right, that we're using linearity. So here I got something wrong. So it says we do not use, okay, so I think I probably got confused myself. Huh? Linearity of U. Okay, that is true. The second one does not use the fact that language. Okay, good. So that's a good point. So we did use linearity, but we were using linearity of T for this property. And for this one, we were using linearity of U. Okay, I mean, I didn't do this one, but you can sort of believe me that, we had to use the linearity for T. So in this case, you have to use it. But, yeah, thank you. I was doubting myself. It seems to be. Okay. Any questions? Good. Okay. So let's continue then. Great. Now what we have is, okay, so the text says that the contents of this lemma and a portion of theorem 5 tell us that the vector space L together with the composition operation is what is known as linear algebra with identity. Okay, this will be discussed in chapter 4. So it's just like a small remark. I also don't fully understand what he's trying to convey here, but I guess the word linear algebra is basically referring to looking at the algebraic structure of linear operators. So that's kind of what we're finally doing. Okay, so example 8 says the following. So suppose A is an M cross N matrix with entries in F. We have the linear transformation T defined by T acting on X equals AX. Okay. So it's going to take N cross 1 column matrices and send them to M cross 1 column matrices. This is just matrix multiplication, right? So this is nothing big. Okay, so suppose that is how you define the linear transformation capital T using this matrix A. And using matrix B, we define the linear transformation U, which is just matrix multiplication with T. Okay? Now, the composition UT is easily described as follows. So UT is going to be, you use the definition of composition. Then you apply the definition of T, you get AX, you apply the definition for U, you get B times AX, and then you can use a composition of matrix multiplication, and that would give you BAX. Okay. So thus UT is basically just left multiplication by the product matrix BA. So this is just giving you an example of explicit example where you're combining or multiplying two linear operators, and then it turns out to be a linear operator, but it's quite explicit. Okay. Another example we look at now is example 9. So it says let F be a field, let V be the vector space of all polynomial functions from capital F to capital F. Okay, and let capital T be the differentiation operator defined in example 2. So the differentiation operator is just basically del by del. You're just removing one of the x's. Okay. And it defines a linear operator T, which is multiplication by capital X. So what it does is it takes whatever polynomial you have and multiplies it by X. Okay, so F is your field, V is basically polynomials, T is the differentiation operator, and T is the multiplier with X. Okay. Now, the claim here is that D times T is not going to be the same as T times T. Okay. So let's maybe see how this would happen. So suppose that we take the function. So let's take fx. So T is what? T is multiplication by X. So let's take T fx to be a constant. Okay. So if you take fx to be a constant, then T of f of x would be what? t of f of x, what would that be? Exactly. Right? So you just multiplying by c or multiplying by x, so you get cx. Okay, and now what would d of t of f of x be? Basically d of x. That's fairly straightforward. Now, the other way, right, if you do differentiation first, what you get a 0, right, in the first step. So you will get, so let's do this, right? So d of f of x, right? So here you get t of, so for c, you're going to get a 0, right? And then 0 times x is going to be 0. So you can see that already for such a simple function, you're not going to get equal. Okay, so it's just like a slightly non-trivial example of saying that things don't always have to commute. And then this one is left as an exercise that if you do dt minus td, you will always get identity. It's basically remove the constitutive accordingly. So you'll always get one. Oh, sorry, one of them will be 0 and the other one will give you a constant. I mean, we actually almost already did that, but yeah, so let's leave it as an exercise. All right, so now let's look at example 10. Actually, no, did I get it wrong? It looks like I got it wrong, right? Because this should have been 1. What did I do wrong here? It should be identity, right? It shouldn't be multiplication with the constant. Or just, oh, it's just sending c to c. I know you're right. Yeah, so it is indeed the case that we started with fx and we got fx here. But we have to prove that if you take a general polynomial, that you would get the same thing. Okay. True. Thanks. Okay, was that clear? What I got confused about, embarrassingly enough. I is identity, right? Yeah. So basically, it's an identity map from V to itself, right? So it has to map functions to functions. Okay. So what I did was I showed that if you have fx equals a constant and you apply this map, you will get the function back, but you have to do it for an arbitrary function. Okay. So that's why I was getting confused. I wanted this to be 1. So that's the thing I was getting. Okay. All right. So example 10 says what? So example 10 is okay. So let's look at it. So it says suppose B is a basis. Okay, it's an ordered basis for a vector space. So alpha 1 to alpha n, whatever. That's fine. Consider the linear operators EPQ. Okay, so we also introduced them for the proof of theorem 5, right? Where we were showing that the dimension of the set of operators would be n. We used a very simple construction. So this is the construction. Okay. And remember what it does, it takes a basis vector Q and replaces it with the basis vector P. Right? So it takes alpha Q, replaces it with beta P, and does nothing or maps the rest to 0. Right? That was the action of this object in Q. Okay. N-square linear operators form a basis for the space of linear operators on V. Right? This is just a consequence of theorem 5 basically. But let's see what they're trying to do here. Okay. So right. Also one more thing is theorem 5 was from V to W, right? Like we were looking at general things. Now W is the same as V. So that's why instead of N, they have it. And these betas are the same as alpha P's, right? Because it's the same basis. Okay. So all right. So then what is this computation? EPQ times ERS. So let's see how to compute these. So you multiply with alpha I, you use the definition, and the definition says that we would get delta IS by alpha R, right? So ERS acting on alpha I would give you alpha. Okay, so we're still using the same notation. So let's just plug in the definition. So here we had so I'm using this definition, okay, right? So it would be delta I times S. So this is the second coordinate. So Q was appearing, right? So I have S here, and then you have alpha p. So instead of p, we have r, the first quadrant. Is that okay? Just applying the definition. I haven't done anything. Okay. Yeah. Okay. So, so we have this step, and now ERS acting on I. Oh, sorry. Okay, so we have this step, and we multiply on the left, right, by EPQ. And EPQ, we can apply the same definition, and we're going to get no, we haven't actually done that yet. So we're just moving things around. So we had EPQ acting on delta IS alpha R. Right? This thing is just delta IS is a scalar. And then we can do the following, right? So I just move things around. And now we can apply the definition again, and I will get delta IS, delta RQ, alpha P. Right? So it replaces it with the pth value, and Q and R have to be the same. So that's appearing in the delta function. Okay. So now when you do this calculation, this is what you get. And so therefore, what we have is the following, that when I matches S and R matches Q, it is only then that you get an non-trivial value. So here it says when Q equals R, you apply the map E on EPS. Okay, otherwise it's zero. So they're basically showing you a composition relation. Okay, is this step here? Because so what is being said is you have delta RQ. Okay, and the rest you can write as EPS acting on alpha I. So this part. So this part calculates like that, and delta RQ. Is that okay? Is it making sense? Okay. Okay, so and so this is exactly the multiplication. Is this clear? Okay, just a bit of calculation, moving the indices around, but this is roughly what we should get. Okay. And then let T be a linear operator on VB. Okay. Now we showed in the proof of theorem 5 that if Aj is written as the coordinates of T alpha j, the vector T alpha j, in the ordered basis beta, and we define A equals the the matrix, right, using these other vectors, coordinates. So if you do that, then the transformation T can be written as a linear combination of EPQs. Okay, so if you go back to the proof, let's go back to the proof of theorem 5. Yeah, let's see where is the expression. So this is what we had, right? So we had written T as a linear combination of these guys. Okay, and remember T alpha j was this object, right? So T alpha j is this object, and what does that mean? This basically means that when you write the coordinates, right, these are going to be EP, so that's A1j, A2j, and so on. Right? So now what they're saying is you put this into a matrix. So that's what they're calling the capital A matrix, right? So A1, whatever the index is, AM. So that's what they're calling the matrix A, and you see that it's just basically matrix multiplication. Right? So that is what is being said. So let's do that. Right. So this is exactly the expression that I showed you a moment ago. Okay. Is that okay? So I know that the notation can get a little bit heavy, but I don't know if this makes sense. Okay. So we have this. Now, if U was this object, so if it was BRS, ERS, right? So it's some other operator, some other linear combination other than A, right? Then the last lemma, let's what? So we had this lemma. What lemma did we use from? Okay, let's just see what the statement is. Actually, I'm not so sure what the lemma is saying here. Okay, so then what we have is TU, right? So TU we can express as the following, and when we expand it out, we would have EPQs, right? E is being multiplied, and then you have these coefficients. This is fine. This is just using the definition that we introduced. Yeah. There was one more person who was following. It's okay, right? Okay. Okay. And then, as we already noted, the only terms that are going to contribute to the sum are where Q and R are the same, right? This is arising from this constraint over here, right? So we said it's only when Q equals R that you're going to get some contribution. Otherwise, it's going to be 0. Correct? So when we expand it, so we have this sum, right? So in this sum, when Q and R are the same, it's only then that you're going to get a contribution. Otherwise, you won't. And also we have that EPR. So EPR, ERS is the same as EPS. Okay, so one just needs to plug the definition, and you will see that the same little r doesn't make it. So this just acts as a limiter. So in the end, this is going to be the same as EPS. So, okay, so the only terms that are going to contribute are where this P and, this Q and R are the same. So Q equals R. So you will be left with P and S. So you have P and S on the matrices A and B, and you have the little r which is common, and you have EPS, which is the multiplication of these objects, right? So you will be able to simplify it, and you will get TU as this object over here. Okay, and what does that tell you? So it tells you something very nice. It says that the effect of composing T and U, okay, which are arbitrary linear operators, is basically to multiply the matrices A and B. Right, because that's the definition of matrix multiplication. You take the rows. Okay. So this is sort of the. So this is an example where we are saying that if you start with arbitrary. If you start with arbitrary linear combinations, a linear operator is EPQ, right? Then. Wait, what did I do here? Give me a second. The point of the example. Yeah, so the point of the example is here. Right? So if you have T as any linear operator, okay, then T composed with some other linear operator U, you can find by basically multiplying the corresponding matrix representations when you express it as a linear combination of these E's, which are the basis of the linear matrix. Okay, so that is what to do. So let me say it again in case you missed it. So the point is that so T we can express as some kind of linear combination of these EPRs, right? And U we can also express as some kind of linear combination of, let's say, QL. So this would be EQL, right? Because these are bases. This we already established. That's sort of the important. Oh, sorry. Did you guys lose the? How long have you not been able to see it? Just okay. Sorry, didn't pay attention. This is fine. Okay. Right. So now, what we're going to do is we're going to. Okay, so in our discussion of algebraic operations with linear transformation, we have not yet said anything about invertibility. Okay, so far we've talked about compositions, whether things are linear operators or not, how you talk about dimensions and so on, but we haven't talked about invertibility yet. And we're now going to look at invertibility. So one specific question of interest is the following: for which linear operators T on the space capital V does there exist some notion of T inverse such that T inverse is the same as T inverse T is the same as identity? Okay, because for matrices we already saw this. We spoke about invertible matrices, right? So now we're going to ask a similar question, but for the set of linear operators. Yeah. Okay. All right. So the notation here is the following. So suppose the function T goes from V to W. Okay. Then we'll call T invertible if there exists a function U that takes you from W to V. Okay, so T is going from V to W. We would call T invertible if if there exists some u, right, which is going from W to V, such that ut is identity on V and tu is identity on W. Is the definition clear? Yeah. Okay. So now the proposition is as follows. So it says that, and we'll not prove this. Okay. So this is something you sort of have to believe for now. There's a proof in the appendix, but I kind of skipped it. So if t is invertible, okay, the function u is unique and is denoted by t inverse. Which is, that's the first property. You cannot have multiple inverses. If it is invertible, in this sense, that ut gives you identity and tu gives you identity, then it has to be the case that the inverse is unique. That's one thing. The other thing is that if t is invertible, it is equivalently, the following statements are equivalent. T is invertible is equivalent to saying that t is a one-to-one map, okay, and that t is onto. So what is a one-to-one map? I guess this all of you guys know, right? That if basically you cannot have collisions, right? So one-to-one map says that if you have t alpha equals some value, then there cannot be another alpha which would give you the same value. Right, with the same vector. Let's call it t. Because that's what this is saying. If alpha and beta give you the same thing, it must be that alpha and beta are the same. Right? So that's one. On to, of course, so yeah, maybe I should clarify this. So in some textbooks, maybe you might have seen something different. So when I use the word range of some operator t, what I mean is it's the set of, say, betas such that there exists alpha for which t alpha is beta. Okay, so it's basically just the image, right? Like everything you can possibly produce. That's called the range, which we'll also call the image. Okay, in some contexts, people confuse range with codomain. We are not going to do that. So it can be that t is a map from, say, V to W, but the image of t is a strict subset of that, right? Which we are also calling the range. So I'm just clarifying notation because some people use the this codomain as range, but we're not going to do that. Just to be clear. Okay. All right. So when it says onto, what it's saying is that the range of t is all of W, right? So the image of t must be the same as W. Okay. So this is basically saying what it means to be invertible. Okay. So a function, so it's an arbitrary function. We've not said anything about it. So if t is invertible, then it's equivalent to saying that t is one-to-one and t is onto. And it's kind of intuitive as well, right? Because you have to be able to go back. So it has to span everything and it has to be unique. Okay. All right. So now theorem 7 says the following. So theorem 7 says let V and W be vector spaces over the field F. Okay. And let capital T be a linear transformation from V to W. Okay. So V and W are vector spaces over F. And T is a linear transformation from V to W. Okay, so T is going from V to W. Now what we're saying is if T is invertible, okay, then the function T inverse is a linear transformation from W to V. Okay, so the fact that T is linear implies that the inverse will also be linear when it is invertible. That is the statement. Is the statement okay? Is it making sense? Okay. All right. So now let's see how to prove this. So we assume the proposition above. Okay, so we're going to assume that this thing is true over here. That being invertible is equivalent to being 1, 1, and 1, 2. And then we'll try to show that if T is invertible and that satisfies those properties, then T inverse would be a linear transformation. So let's start. So here beta 1, beta 2 are vectors in W, okay, and C is a scalar. So beta 1, beta 2 are in W, C is a scalar. And what we want to show is that when you take T inverse on some, the standard property, right, for showing that something is a linear transformation, So we want to argue that T inverse acting on C beta 1 plus beta times T inverse beta 1 plus T inverse of beta 2, right? That's just the definition. Okay, so now let alpha I be the same as T inverse beta I. Okay, so alpha 1 is T inverse beta 1, alpha 2 is T inverse beta 2. Okay, and now let alpha I be the unique vector in V such that T alpha I is the same as beta I. Right? And this has to be unique because otherwise T inverse will not be unique. Right? Like, so you'll get multiple inverses, so you cannot do. Okay? So alpha I is such that, yeah, so T alpha I is beta I. Okay, so you also define this vector alpha I. Now it says that since T is linear, what do we have? We have T C acting on alpha plus on beta, on alpha 2, is the same as C acting on these transformations individually. Okay, so it would be the same as C T alpha 1 plus T alpha 2. And what are these objects? These are by definition beta 1 plus beta 2, right? So this is fine. And now the point is that, so that therefore C alpha 1 and C alpha 2 is the unique vector in V that is sent by T to C beta 1, C beta 2. So what we did is we first argued that there would be exactly one vector that would give the corresponding mapping. And then we found one vector that does give the mapping. So we know it is the only vector, okay, from uniqueness. So we know, so we have this vector. We know that this would give us the required mapping. And so therefore, what do we have? We have that when you apply T inverse to C beta 1, beta 2, you're going to get this object over here, right? Which is what we just proved above. And what is this object itself? So alpha 1 on alpha 2, one can replace C T inverse beta 1 and C T inverse beta 2, just from the definition. Okay. But that's exactly what we wanted to argue, right? We wanted to argue that T inverse, when you apply converse combination or this linear combination, would give you the corresponding combination. Is it okay? Okay, fantastic. Right, so this establishes the T inverse is linear. Okay. Right. So moving on, so suppose that we have an invertible linear transformation from T to V, linear transformation T from V to W. Okay. So this is invertible and linear. And we have an invertible transformation again from W to Z. Okay. This is also invertible. So the question is, what can one say about the composition UT? Okay. And the claim is very, very simple. So the claim just says that UT is also invertible, and in fact, this is the inverse. Because it's very much like how we do it for matrices. Right? For matrices, also when you write the inverse, it looks very much like this. And the reason is exactly the same because when you take the composition, you apply the definition, not definition, this conjecture, this claim, right? That this is the inverse, and you will see that it gives you identity in both cases. Right? Doesn't matter whether you multiply it on the left or the right, both cases it gives you identity. And so what that means is that it is invertible, and this UT inverse defined as such is the inverse. Okay. And we have to note that we did not rely on whether U inverse and T inverse are 1-to-1 or 1-to-2. Okay. And it did not rely on linearity. Okay. The only thing it relied on was that you have the inverses for these objects. And that is enough to show that the composition would also be invertible. Okay, it's just a small example. Okay. Any questions about this? This part should be very straightforward. Is it okay? Okay, right. All right, so let's continue then. So if T is linear, then T acting on alpha minus beta is going to be this object. This is fine. This is just by linearity. This is true. Okay. And therefore T alpha and T beta have to be the same. Sorry. If T alpha equals T beta, then this is equivalent to saying that T alpha minus beta is 0. Right? So this is sort of a very nice property about linear transformations, right? That if you want to check whether the map has any collisions, you can check whether the kernel has any elements, kernel or the null space. Okay, so I should also clarify that we use the word kernel of a map T to be the same as the null space of a map T. Okay, and these are defined to be vectors. So let's use the same notation. So alpha such that T alpha is 0. Okay. So for an arbitrary map, when I use the word kernel or the word null space, or the phrase null space, whatever, they refer to the same object. Okay. So now what we're saying here is that to check whether two different images, sorry, two different pre-images map to the same image, okay, it is basically enough to check whether the kernel is empty or not. Right? Because if there were two distinct pre-images, so if there existed alpha not equal to beta, such that T of alpha equals T of beta, right? Then this would imply that T of alpha minus beta is not 0. Oh, sorry, this T of alpha minus beta is 0, right? Because we are using this fact and linearity. Yeah, no? Okay, and what does that tell us? That tells us that you have, so this is not 0, right? Because alpha is not equal to beta, right? And so what does that mean? That implies that so alpha minus beta belongs to the kernel of T, correct? Is that making sense? Okay. So that is sort of the main point here, that to test whether something is one-to-one, if you're guaranteed that the map is linear, you can relate it to the nullity of the. That is sort of what. Is making sense? No. If something not clear, you can ask me. I can happy to repeat. All right. So then let's continue. So here the notation that we are using is the following. So a linear transformation capital T is called non-singular if T gamma equals 0 implies gamma equals 0. Okay. So in other words, it's just saying that the null space has only one element. Okay. So the only vector, so the only element that would give you 0 is the 0 element itself. Nothing else will give you. Yeah. So nullity is the dimension. The dimension is 0, right? Like it's we had a question like this in the question, because otherwise the rank nullity theorem will go wrong, right? Where we were summing. So rank nullity, remember, rank plus 1. But what were the letters I keep getting confused? I think N. So one of them is rank. Is this rank? Or is this nullity? I guess this is nullity. Probably not, right? Okay. Okay, I forget the letters, okay, but the point is rank plus nullity has to be N. And like if everything is like full rank, right, then nullity is 0. Has to be. You can't take it to be 1. That's what I'm saying. The 0 vector does not contribute 0 to the dimension. You have to have a non-zero element to okay. All right. So evidently T is 1-to-1 if and only if T is singular, non-singular. Sorry. Right. This is what I was explaining earlier. Right. So clearly, if T is not 1-to-1, there would be two distinct elements. So there would be alpha. This is exactly what I was saying actually here, right? So if it is not 1-to-1, it would mean that there would exist alpha not equal to beta, right? Such that they map to the same object, say C. And so the difference would be 0 by linearity. And that would mean that you have an element in the kernel. Yeah, that means that nullity is non-zero. Is that clear? No, it's not clear for everyone. Is it clear for you? You're not convinced? No? Okay. I'll go through it one more time. This is very, very simple, but it's good to sort of clarify it. So what we are saying here is that, so let's do the proof again. Okay, so let's give what we said earlier. So if T is not 1-to-1, what does that mean? So it means that there exists beta prime. Okay, so let's say beta distinct from beta prime, okay, such that T of beta equals T of beta prime. That is what it means to be not being 1-to-1, right? So you have two elements, beta and beta prime, that are being mapped to the same element, right? Under T. Is that okay? Wait, the people I'm explaining it to are not listening. The others actually already know. Is it making sense? What's his name? Is it making sense? What's your name? Say it again. Karthik. Okay. Is it making sense, Karthik? Because you were following along, but you seem to not follow this part. So I thought I'd just ask. Is it making sense? Okay. So what you're saying is that if t is not 1 to 1, right? What does that mean? So there are two elements, beta and beta prime, right? That get mapped to the same object. Right? That's what it means to not be 1 to 1. Is that okay? So there exists beta prime that are distinct such that under the mapping T, they map to the same object. Let's call it say gamma. Right? Okay. Now T of beta minus beta prime, because T is a linear map, we can write it as T of beta minus T of beta prime. Is that correct? So what is this equal to? Karthik, what do you think? It's 0. Right? Exactly. So okay, fantastic. And beta minus beta prime, they're not the same vectors. So it's not right. So this is a non-zero vector. Okay, so now what do we have? So let's call this say beta double prime. So we have beta double prime is such that when you act with T, it gives you 0. Okay, so what does this mean? Beta double prime belongs to the, does it or does it not belong to the kernel? Right, correct? So it belongs to the kernel of T. And if something belongs to the kernel, what does that mean? That it's singular, right? Because there is some non-zero element. Okay, that's all the theorem says. Is that okay? Next time, just ask. Okay, don't fall behind. The whole point is for you guys to learn. Some of you will understand immediately. Yes, I'm sorry. So you have to just wait through it. But okay, got it. So let's continue. So now the point is that the extension of this claim is that non-singular linear transformations are those that preserve linear independence. Okay. So intuitively, what it is saying is if you have some linearly independent vectors, a non-singular linear transformation is going to preserve that linear independence. Okay, it will not make two linearly independent vectors into the same vector. Okay, that is how we intuition. So let's formalize this. So the theorem says the following. So let T be a linear transformation from V to W. Okay, then the following are equivalent. So T is non-singular is equivalent to saying that T carries each linearly independent subset of V into a linearly independent subset of W. Okay, so these statements are the same. They might not look the same, but they turn out to be the same. Is the statement clear? Yeah. Okay. All right. So now let's look at the proof. So first we're going to prove that if T is non-singular, that would imply linear independence is preserved. Oh, I've written it down. Linear independence. Okay, so let's see how to prove that. So right. So let S be some linearly independent subset of V. So S V, which is linearly independent, means that if alpha 1 to alpha k are vectors in capital S, okay, then the vectors T alpha 1 to T alpha k are also linearly independent. Okay, so you already know that the vectors in S are linearly independent. Now we're going to apply the map T and take them from V to W, and we're going to argue that these new vectors are also linearly independent. That is what the, how do you prove this? So suppose there are some scalars C1 to Ck, okay, such that when you take linear combinations of these vectors in W that you just treated, okay, suppose they were 0. Okay. So to show linear independence, we have to argue what? We have to argue that the only way this can happen is when all C's are 0. Right? That's the only way this can happen. So how do we do it? Okay, so let's apply this. So we have T, and we apply this map, and it still has equivalent because T is, yeah, so T is linear. Right? So these statements are equivalent, correct? Okay. Now, finally, since T is itself non-singular, what does that mean? It means that The only way something would map to 0 is if this vector itself was 0. Right? Okay. And what does that mean? Now recall that C alpha k's, alpha i's are linearly independent. Right? So therefore, the only way this statement can be true is if the C's are 0 individually. Okay. And what does that tell you? That tells you that, well, this vector, so any arbitrary linear combination that you do, the only way they can give you a 0 vector is if all the C's were 0, which is what we wanted to argue. Okay, so that shows that these T's are indeed linearly independent, as we put it. Is fine? Okay. So now, okay, so this claim shows that the image of S under T is independent. Okay, independent meaning the same, linearly independent. Okay. Now let's do the other direction. So suppose that the independent set S is mapped to an independent set under T. This would imply that T is non-singular. Okay, so let's see how to prove this. So let alpha be a non-zero vector in V. Okay, so alpha is in V and alpha is not 0. Okay. Define S to be this single set. Okay, so S consists of just one vector. Okay. And this by definition is independent, right? Because a set with a single vector, it satisfies the definition. The only way this can give you 0 is if the vector is 0. Okay, and remember, this is somebody was making the yeah, okay, fine. That's not very good. It's fine. Okay, so this is fine. Now the image of S is basically just this set. It's T alpha. Right. So S under T gets mapped to T of alpha. That's all there is. Right. Okay. All right. And now this is guaranteed to be independent. We assume that images of S under T are independent. We assume that is what we are trying to do, right? We are saying, suppose it were the case that T is such a map that it will map independent sets to independent sets, right? So that is by assumption. So S will, because S is independent, it will be mapped to something that is linearly. Is that okay? Well, so if this set is, this vector in particular cannot be 0 because the empty set is not linearly independent. Or the set with the 0 vector is not linearly independent. Okay. Okay, and so then what we get? So we get the fact that the null space of T is the 0 subspace. Yeah. So what is the definition of a null space? It was alpha such that T alpha is 0. Regardless of which alpha you take, which non-zero alpha you take, T alpha cannot be 0. Right? This is what we just observed. So that means that the kernel has to be essentially just a 0 vector. Okay, is that right? Do you want me to repeat it, Karthik? Is it clear? No, did you get lost somewhere? Tell me. Yeah, for sure. That's the whole point. Okay, so what we're trying to argue is that if you're mapping independent sets to independent sets, right? So if T is a map, so T is such that independent sets are mapped to independent sets. Okay. Then we want to prove that T is non-singular. Non-singular meaning that the kernel of T has exactly the 0 vector. Right? Because singular means that the kernel has non-zero vectors. Okay. So how do we prove this? So we start with the following. So we say, suppose alpha is a non-zero vector in. So you take any arbitrary non-zero vector in V. Okay. Now you define the set S consisting of just one element. Okay. So we're going to define S to just be the element of one vector. Exactly one vector. It has nothing else. Okay. Now the question is S independent? Okay. And this might look a little bit tricky, but it is an independent set. Right? Because the only way this gives you 0 is if you multiply alpha with 0. There are no other vectors to add. Right? So that's why. So this is independent. Now we are guaranteed, right, from the premise, right? So we said T is a map such that it maps independent sets to independent sets. So we know that TS, so T of alpha, okay, so let's call this S prime. So this will also be independent. Right? That's because that's what we assumed about t. Okay, so this is independent. Now, because it is independent, we know that t alpha cannot be 0. Because if it was 0, then it is not independent. It's a dependent set, right? Okay, but that essentially completes the proof, right? Because we wanted to argue that the kernel of t can only have the 0 vector. And we just argued that regardless of which vector you take, it cannot be 0. It cannot give you 0 under the mapping of t. The only way it gives you 0 is if alpha is alpha, which is what we want. Okay. Okay, so let's continue then. Okay. So now we said that a linear transformation T is 1-to-1 if and only if T is non-singular, right? And we also said that T is invertible if and only if T satisfies these two properties. So this was one of the, I think it was one of the propositions. Let me remind you quickly. Yeah, so this proposition is the one I'm talking about, right? So T is invertible if and only if it is 1-to-1 and not 2. That was one property, right? And the one above was basically, okay, so this is the property that we just discussed. And we said that T is 1-to-1 if and only if T is non-singular. That's the thing that we just discussed, right? Because if it's not, like, it's somewhere here. This one, right? Those are the two properties I'm talking about. Okay. So now what we're going to do is we're going to explore whether it can be the case that there is a singular T, okay, and yet it has some kind of an inverse. Okay? So far everything seems to suggest that the only way you can have an inverse is like if things are 1-to-1. So and 1-to-1 basically corresponds to being non-singular. So now we're going to ask, is it possible that there is some map which is singular and nonetheless it has some kind of inverse? So let's see if we can do that. So in this example, we're going to actually find, so we're going to see such a thing. So suppose F is some subfield of complex numbers, right? We can even pretend it's complex numbers, that's fine. And let V be this space of polynomial functions defined over capital F, over the field, right? So F is a field, non-zero characteristic, or something. So you can say subfield of complex, right? This is fine. The first point. The second point is now you consider V to be the space of polynomials over that. Okay? And now we're going to consider the same differentiation and multiplication by T operator that we had considered in one of the examples before. Right? So D is differentiation and T is multiply by X. So now let's look at operator D first. So because D of any constant C, so when you evaluate it, what do you get? You get 0, right? So since D sends all constants to 0, we know that D is singular, right? Why is it singular? Because the kernel of D at least contains 0, 1, 2, basically all elements of the field, right? So C belonging to that, right? So we know that the kernel is non-empty, so it's certainly singular. However, V is not finite dimensional, right? Because now we are applying it on polynomials, and polynomials we had an example, right? That it's an infinite dimensional vector space. It's not a finite dimensional vector space. So even though the kernel is actually non-zero, so there are elements, so the map is singular, we would still be able to find a right inverse for this map. Okay, and that is a little bit surprising, given everything that we have. Okay, so for instance, if E is the indefinite integral operator, oh no. Okay, I have no idea what I had to do. But I guess indefinite integral operator we know, right? Like you basically integrating it. So it's just the integration operator. Okay. Then E is a linear operator on V. Okay, this is sort of standard. Like if you're integrating from 0 to 1, f of x, that is the map. Okay, so this is the map of V. Oh, it's indefinite, sorry. So you just integrate, right, and you get some answer. Okay. Then the claim is that DE is going to give you identity. And this we know very well from calculus, right? Like if you integrate something and then you differentiate it, you'll get the same function. That's not surprising. Okay. What is surprising is that the map is singular, and even then you can find a right inverse. Okay. Uh-huh. Yeah. So okay. So what we are saying here is that D is not finite dimensional, and the range of D is all of V. So D, yeah, because I actually didn't emphasize this point. So V is not finite dimensional is clear, right? Because it's acting on so the input is basically, so it's a map from the set of polynomials, right, to the set of polynomials. So we were calling it from V to V. But it could be, like, so for example, one can consider a map that doesn't actually span all of V. Right? Like maybe it sends everything to 0, for example. Right? So then it will not span V, but here it spans V. So the range of D, meaning the image of D, is actually going to match. Because for whatever function you like, you could construct a new function whose differentiation would give you that function. At least polynomials. We are restricted to polynomials. Okay, not in general, but for polynomials, this is the case. Right? We just multiply with x, or whatever. You'll get it. Is that okay? So that is sort of the insight that even though you have the map is singular, you can still have inverse. Okay, I think that's maybe a good point to stop here. Do you have a question? Yeah, okay. So it turns out, so what we're trying to argue is that it turns out that it is possible to define a right inverse for T. Okay. How do you define the right inverse? Well, I mean, this you already know very well. So denote by E the indefinite integration. It is just this. You integrate fx dx. That's it. So for polynomials, you can even express it explicitly. Right? We know what the expression is. It turns out that E multiplied with D would give you identity. Right? Because you take any polynomial, you integrate it first, and then you differentiate it, you get the same polynomial back. Right? So this is like a very surprising thing that even though the map is not singular, right? It has the map is singular, it has things that it's sending to 0. Even then, you're able to find an inverse to this, which was not happening in the finite dimensional case. Okay. So I guess, yeah, this is a good point to stop. Sorry, I'm 30 seconds beyond the scheduled time. Sorry. Okay. Thank you.